In the space of matrices and any subspace involving matrices, linear independence works kind of like it does in Rn. In any space of polynomials, linear independence works kind of like it does in Rn. But in the space of functions, linear independence is more involved. So let's look at what we have to do to decide if a collection of functions is linearly independent. So let's say we have functions f1 of x through fk of x. Let these be functions defined on an interval capital I. We'll call them linearly independent. If the only linear combination C1 f1 of x plus dot 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 plus ck fk of x that equals the zero function, so by that I mean equals 0 for all x in the interval I, is the zero linear combination. 0 f1 plus 0 f2, etc. up to 0 fk. Certainly that's going to be one linear combination of the functions that's equal to the zero function. No matter what x you plug in, you get 0. So we'll call the collection linearly independent if that's the only linear combination of the functions that's equal to the zero function. All right, and as I said, there's a difficulty that's going to make this different than analyzing vectors in Rn or a space of matrices or a space of polynomial functions. These are arbitrary functions, and they can be trig functions and square root and exponential functions, etc. Then the space of all functions on I has no finite spanning set. So that means that we can't represent each function as a column vector. And that's true even if we restrict our attention to continuous functions, and it's true even if we restrict our attention to differentiable continuous functions. Now, there's a partial remedy to this difficulty. Not perfect, but it'll be good enough in some situations. We're going to replace each function by a vector of its derivatives. Now this is only going to work if we have differentiable functions. So assuming the functions are differentiable on I. And actually we're going to use the first k minus 1 derivative. So not only do they have to be differentiable the first time, but they have to be differentiable a second time and a third time all the way up to k minus 1. So k minus 1 times differentiable. So I'm saying replace the function fi of x with, let's say, a vector vi, which is f of x, first derivative, second derivative, all the way down to the k minus first derivative. Then with the k functions, we can create a k by k matrix by using these as the columns. So we can define a k by k matrix A, whose columns are v1, v2, etc. up to vk. One column for each function. Well, this should be fi and its derivatives. In some other column, the jth column, of course, it would be fj, fj prime, fj double prime, etc. Then we're going to take the derivative of this, and we'll call it w of f1 through fk. After the inventor of this method, so this is the Wronskian of f1 through fk, which is just the determinant of A. Then the fact is, if the Wronskian determinant of A is non-zero for at least one value of x, then that means that this set of functions is a linearly independent set of functions. And the reason that works is, so if w is not 0, that is, determinant of A is not 0, then A is invertible. then the only solution to a c bar equals 0 bar is c bar equals a inverse 0 bar, which is just 0 bar. And the first row of A, so we've got the functions in the first row. So the first row of the system of equations is the first equation is C1F1 plus C2F2, etc. And the other rows are just consequences of this. So the ith row is C1 ith derivative of F1 plus C2 ith derivative of F2, etc. So if the only way to make all of these 0 is to take all the coefficients to be equal to 0, then the only way to make the first one equal to 0 is to take all those coefficients equal to 0. Each one of these derivative equations just follows from the first. It's not really any more information. Now another fact is that if W equals 0, that is the determinant of A equals 0, then we have no information. So the functions might be linearly independent or they might be dependent. And the fact that this doesn't give us a perfect test, yes or no, is why I said it's a partial remedy before, not a perfect remedy. But let's look at one example where it does work. So for example, we might ask, are sine x, cosine x, and e to the x linearly independent? Now these functions are defined everywhere from negative infinity to infinity, so we can use that as our interval where they're defined. So to answer, we'll compute the determinant of the first row is going to be sine x, cosine x, e to the x. The second row is going to be derivatives of these. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of e to the x is e to the x. And then second derivative. Derivative of cosine is minus sine. Derivative of minus sine is minus cosine. Derivative of e to the x is e to the x. Now we get to use a fact about determinants that I don't use that often, which is that you can factor something out of a column and just bring it out of the determinant. So since our third column is all e to the x, we can factor an e to the x out of here and say that's equal to e to the x determinant of, and just replace those with 1s. Sine x, cosine x, 1. Cosine x minus sine x, 1 minus sine x minus cosine x 1. And then we get e to the x times negative sine squared negative cosine squared minus sine x cosine x minus, so minus sine squared and then minus cosine squared and then minus negative sine x cosine x, so plus sine x cosine x. And that equals e to the x times minus sine x minus cosine squared x is negative 1. Minus sine squared x minus cosine squared x is another negative 1, so I might as well write negative 2. And then minus sine x cosine x plus sine x cosine x is 0. So e to the x times negative 2. Which is negative 2 e to the x. And now we have to think of a value of x that makes that non-zero. Well, e to the x is never 0, so we can plug in anything we want. Negative 2 e to the x is not 0 when, for example, x equals 0. It is negative 2 e to the 0, which is negative 2. I could have plugged in x equals 1, x equals negative 1, anything really, because negative 2 e to the x is never 0. So since this matrix had a non-zero determinant for at least one value of x, that means that sine x, cosine x, and e to the x is a linearly independent set of functions. Now when you take a determinant and get that it's always 0 and therefore end up with no information, that's not as interesting, but it's probably worth looking at that happening in the book once. So let me just say see book example 4524b for three functions which have their Wronskian equal to 0 but are actually linearly independent. So this would be an example of where the Wronskian test fails. We don't get any information. So if the Wronskian is 0, no information. If the Wronskian is non-zero for at least one value of x, then we know that our functions are linearly independent. The end.